Hallo und herzlich willkommen zur 10. Folge des All-Day Research Podcasts, der euch dabei helfen soll, schnell und effizient in die Welt der Forschung einzusteigen. In der heutigen Ausgabe begrüßen wir Prof. Dr. Sevag Gharibian. Zusammen mit unserem Moderator Lukas Ostermann sprechen sie über das Thema Quantencomputing. All-Day Research Podcast.
Damit auch herzlich willkommen von mir zur nächsten Ausgabe vom All-Day Research Podcast. Mein Name ist Lukas Ostermann und heute geht es um das Thema Quanteninformatik und dazu spreche ich mit Prof. Dr. Gharibian. Hello, thank you for coming.
Hallo.
Diese Folge werden wir heute auf Englisch aufzeichnen. Dementsprechend wundert euch nicht, dass ich jetzt die Sprache wechsle. Genau. So, the first question I ask the professors is, like, where do you study and what were the stages of your academic career until you came to Paderborn, and maybe where was also the first contact with your research field?
Okay, that's very good. That's a nice question. So I grew up in Canada, so I did my all three of my degrees, bachelor's, master's, and PhD at the University of Waterloo, which is essentially nowadays a hub for quantum computing. And after I finished my PhD there, I went to the University of California, Berkeley to do a postdoctoral fellowship for about a year and a half. Then after that, I was in Virginia, working as a faculty member for 3 years. And finally, in 2018, I came here to Paderborn. And since then, I've been here, basically. And my first interaction with my research field actually was complete coincidence, complete accident. I was doing my homework. Students listening should not copy my example, I suppose, but I was supposed to be doing my homework and I didn't feel like doing it. So I was wandering the halls in our math building, and one of the professor's doors had a plaque said Institute for Quantum Computing. And I thought this was really interesting. I was like, what is this? I have no idea what this is. And so I knocked on his door. He happened to be there and he opened the door, and that literally changed the course of my life. So we had a discussion. He told me what I needed to get into the field and so forth. And it was one of those moments that changes your life, kind of.
Yeah, that sounds great. And it also sounds like a huge step to move from like North America to Germany.
Yeah, I suppose that's true. I mean, I do have part of my family is German, so there's a certain level of comfort that's built in, right? Let's say. And, I wasn't born in Canada. I have a very long history of kind of moving around, let's say. So it kind of wasn't that unnatural, I mean, in some sense, right? But Germany is also a great country to come to. I mean, you're not, it's a good step to make, I would say, right? The quality of life is high, and I really enjoyed the academic and the social atmosphere here, in fact.
So, like, did you study computer science, or was it already like some quantum computing?
Oh, no. I did computer science. I didn't even want anything to do with mathematics and theory when I was a student. I wanted to be a programmer, and I actually did that. I graduated, and then I was a programmer for a year and a half, and I realized I just didn't like it. Right? And I needed a bit more of a challenge. I needed something that stimulated me in terms of problem solving a little bit more. And so I went back for my master's, and that's kind of how this started. Right?
Oh, okay.
But at that point, I knew about quantum computing. I just hadn't decided yet that, I want to really dedicate, the next 6 years of my life to get a PhD, let's say, or whatever, right?
Sounds great. We will talk about that in a second, but
Sure.
First of all, I will like to do some either-or questions. I'll do to every professor. So the questions would be starting with beer or wine?
Beer or wine? Normally I would say neither, but I don't mind. A good white wine is very nice. So let's say that. But I mean, they're both fine. I'll drink both occasionally. Let's put it that way. Yeah.
Mountains or sea?
Mountains. Yeah.
Hardware or software?
Hardware or software? I guess I have to say software, yeah. I mean, that's closer to what I do, right? So, yeah.
Theory or practice?
Theory.
Your data in the cloud or on your own hard drive?
Certainly my own hard drive. And not for privacy reasons, just because it's with me, and then I could, in case the internet's down, I don't have to worry, right? I'm not a privacy person. I'm more practicality, let's say.
Coffee or tea?
Both. Now it's coffee. It used to be tea. Now I've switched to coffee. Yeah.
Typical German thing, I would say.
Is that true?
Yeah, kind of. I think
interesting.
coffee is like typical German drink.
Oh, that's true. Yeah, the Germans are very fond of fruit teas, I find, which is not a real tea, technically speaking. But coffee is big here. Yeah, that's right. Yeah. Well, coffee's great. I'm not complaining. Yeah.
The last one, written or oral exam?
Always written. Yeah, oral is... I mean, I understand the pros of oral. Okay, well, maybe I'm okay. We don't do oral exams in North America, so it was a new concept to me when I came here.
Okay.
So that's why I say written as my first response, but it's also, if you have a large class, it's a total pain to it's much more efficient to just have a written exam. Yeah. But if you have a small number of students, oral is nice. You could lead them through the questions. They could learn from you a bit. And so I maybe they're both equal, but they both have places where they get used, I think, and where they shouldn't get used.
I mean, if we have the opportunity, maybe you can talk about some things in North America, how the system there works.
Oh my God,
in comparison to the German system.
Okay. I was just complaining about this yesterday, so it's the right time for this question. So it drives me crazy here that in Paderborn, and I think this is not just our system, but it's NRW's system, which is that the exams, you're allowed to write them multiple times. There's more than one sitting. So if you just don't feel like doing the first one, you just don't do it. And then you just go for the second one. This doesn't work in North America. In North America, at the beginning of the semester, there's one single exam time that's set by the central administration, and everybody writes at that time, on that day period. If you pass, you pass. If you fail, you fail. You take the entire course again. And that's it, right? And here it's very frustrating because I have to write, let's say, 2 versions of an exam for each offering of the course. And if just one student doesn't go to the first sitting of the exam, now I have to write a whole second exam just for that one student, right? I mean, so it's a lot of work. A lot of students just are scared and they just don't take the exam. They wait. And, it just drags everything out, I find. So I strongly dislike that. One thing I like more here is that the students are a bit more self-sufficient. In North America, people tend to hold your hand a lot more. So a perfect example of this is when I came in as a faculty member to North America. I mean, there was a lot of information about how I should adapt to the job, and they had information sessions and whole day, events. And here I just kind of sat at my desk and they said, okay, figure it out. And then I just had to talk to people. And so, I mean, it gives me an insight into the culture and how things are expected to be done in some sense, that you're expected to be more independent. And I certainly notice that in my students here. Like when I'm looking for research assistants, like the mindset of the students is different here. So this I really like, let's say. Yeah.
Okay, thank you for this comparison. And now I would say we start with your research field.
Sure.
Maybe you can tell us how you would define your field of research and maybe what are the challenges in that.
Okay. So I study quantum computing. Now that's a very broad term. I mean, because the field of quantum computing encompasses everything from, of course, physics, both theory and experiment, to engineering, to mathematics and computer science. So it's very, very broad. It's very interdisciplinary. And that typically means that to enter the field takes a bit of work. It's something where you have to build some background first in various topics before you can start to get into the literature. So what do we do? I mean, we're trying to build quantum computers, right? These are computers that are don't work in the same way that our current computers work. They work according to a different set of physical laws called quantum physics. And so what that means is that roughly we now have to, not me, I mean, I don't build these machines because I'm not a physicist, but what the challenge is essentially is you need to control subatomic particles. So you need to control, say, atoms or electrons or photons, whatever your system is based on, whatever platform you're using, you need to have very, very fine control. That's incredibly difficult because nature doesn't like to be controlled at that scale. It's very hard to keep the system noise-free, let's say, to keep it doing what you want it to do for a very long time. And that's the physical side of it, right? People who actually want to build these devices. And of course, what we do here is we work more on the theory side. And what that means is that we say, okay, imagine I could build a quantum computer at a large scale. What could I do with it, right? What problems can I solve with it? Especially algorithmically, right? Like computational problems. And so that's more along the lines of what we focus on here.
So this is more theoretical.
Yeah.
One question would be, how do you work with quantum computers if you don't have one?
Oh, that's a very good question, actually. So I always like to say, like, when it comes to theory, there's theory world and then there's the real world, right? And there's usually a big divide between them that theorists tend to overlook. But what we tend to do in theory is we put down a mathematical model that is a pretty good approximation to what actually happens in nature, right? Or in the lab, let's say. And so what that means is that, we work with a version of quantum mechanics that is a very good approximation to what actually happens in a lab. But it's a pretty clean description of, these rules of quantum mechanics are just a set of mathematical laws you can write down, and then you're just in math world, right? I mean, you can forget about quantum mechanics, what it means, how the devices work. It's just, if you want a little bit more details, we're basically doing linear algebra. So we have matrices, we have vectors, and we just multiply them. If I'm going to make it very simple, that's all that happens, right? And it turns out that you can model the subatomic world quite well using this kind of formalism, basically. So that's how we do it. We're living in this kind of magical world where, imagine we can do all of our quantum operations perfectly. Let's say there's no noise in the system. We can prepare whatever state we want in the right, well, not whatever state we want, but, if I have a circuit that does something, I can assume that it will actually work as I want it to. In real life, of course, it doesn't go that way, right? In real life, you have to worry about errors, and there is a whole field in theory also dealing with errors, of course. But at least in my side of the research, we assume things are kind of perfect. And then we ask, what could the perfect quantum computer achieve or not achieve, right? And you also try and show that even if you had like a perfect quantum computer at a large scale, there are some problems that you just can't solve efficiently, right? So...
Sounds like maths is like a big part of your research as well than computer science.
Yeah, absolutely. Itself. Yeah. So we basically are more like applied mathematicians, I would say.
Okay.
And part of the problem in designing things like quantum algorithms is that a lot of times it's not very intuitive. Classically, if you're designing algorithms, it sort of makes sense that if you want to solve, let's say, a search problem on a graph, you might split up the graph in a certain way, and there's some intuition as to why that should work. But quantumly, most algorithms, they're mostly mathematical tricks. There's no good intuition as to why this should work before you actually try it and you do the math and you see, oh, actually it does work, right? And so it's a bit counterintuitive. It's difficult in that regard.
You talked about quantum algorithms.
Yeah.
I mean, like a normal algorithm is pretty simple, I would say, like in a way to understand, but like, what exactly is a quantum algorithm? Like, what is the difference between like a normal algorithm and a quantum one?
So I can explain it in a relatively simple way, which is just that classically, anything we can do, say efficiently or in polynomial time, let's say, if you want me to be a little bit more precise, on a polynomial time Turing machine, we can do using a polynomial sized circuit, right? And typically, in hardware, you're dealing with circuits, right? I mean, nobody actually uses real Turing machines, right? That's ridiculous, right? So what we do is like, we copy this idea, right? So classically, if you have a circuit, if you could do and not gate, that's universal. You can do any classical circuit now. And so we have a similar idea. There's a notion of, instead of a classical circuit, it's a quantum circuit. And just like classically and not is universal, there's some corresponding set of universal quantum gates you can apply. Those include all the classical gates. You can do like a classical and, et cetera, et cetera. But now you get a much bigger set of operations you're allowed to apply. And really the only restriction is that in quantum mechanics, I'm generalizing, but typically operations have to be reversible, right? Which classically they're not, but you can model them in such a way that they become reversible. And so that gives you a lot more flexibility to do things. Like you can apply quantum gates that put your register or your quantum bit into two different states at the same time, for example, like 0 and 1. And that's, of course, something you can't do classically, right? But, at a very high level, it's just a different gate set you get to play with. If you want to understand how we actually work with this, it's quite simple. Each gate is just like some matrix, and your quantum state is a vector. And then so to apply the circuit, you just take your vector and you multiply the matrices one by one for each gate. This is the way it works.
Like just a simple function you apply on like a vector.
Yeah. And of course, the hard thing is designing a good circuit, right? That so that when you take your vector and you multiply by these matrices, the resulting vector has the property you want, right? That's not obvious.
Maybe we can talk about like the benefits of that. So
Yeah.
maybe the listeners now know what like a quantum algorithm is.
Yeah.
But what are the benefits of that?
Okay. So as I said, you can do more things with a quantum circuit than you can with a classical circuit, because a classical circuit is a special case. In the quantum setting, you have access to a much larger set of possible gates you can apply. This is the basic premise. And so, of course, that means that in principle, you can do, at least you can hope for things you could do on a quantum computer that you cannot do classically. So the most famous example of this is Shor's factoring algorithm, which basically says that if you give me a very large integer, so for example, if I remember that if I write down an integer using n bits on a Turing machine, right, then the magnitude, the size of this integer scales like 2 to the n. It's exponential in the input length, right? So normally if I give you a big integer, right, and I ask you to break it into its prime factors, this is very, very difficult. We don't know how to do this classically. In fact, most crypto systems in use today, like RSA, use the assumption that factoring is hard.
Yeah.
And so it turns out that, surprise, surprise, in 1994, Peter Shor comes along and says, if you could build, a large-scale quantum computer that works as it should, then you could break the factoring problem. You can solve it efficiently. And so, this was a very big deal because, everybody had been relying on RSA for like 20, 30 years at this point, and we still do, right? And so that's a perfect example of a problem where even theoretically, we don't know or we don't believe that this problem can be solved in polynomial time, right? At the same time, we also believe that it's probably not likely to be an NP-hard problem or something like this. So it's one of these funny problems we call NP intermediate, which is it's not necessarily NP, but it's also not NP-hard. We don't really know what to do with these things right now.
You talked about NP, like for people who don't know, there are like two main complexity classes of problems, like P and NP. Just like if we want to keep it simple, like problems we can solve in a time that it's usable, and problems that will like maybe they are solvable, but it would take like such a long time we cannot like do it today. Maybe you can you said that we can solve problems that are probably in NP with quantum computing. Is that right? Or
so I should clarify. So NP, okay, so good. So NP is the class of problems, roughly speaking, that computing the solution to your problem is not necessarily easy. It could be easy, like you said. But what is easy is to verify the solution if I give you the solution. So that's kind of the defining property of NP. So it includes both easy and hard problems. So the perfect example that's typically given is something like Sudoku, like one of these like puzzle games, right? Where if I give you a Sudoku puzzle and I ask you to fill it in with the numbers to satisfy the rules, then this can be very difficult. It's not obvious how you do this. So it's not obviously in what we call the complexity class P. But if I instead fill out that Sudoku puzzle for you and I give you the solution, I say, check it, is it right? Then that's very easy for you to check. You just check that the numbers, follow the rules.
Yeah.
And so that's NP. It's everything we can check the answer to, but maybe coming up with the answer is very, very hard. And so in quantum computing, there are some problems like the factoring problem that we can solve, efficiently, meaning, like you said, on a time scale that is maybe a few hours, let's say in theory, versus, the lifetime of the universe if the number to be factored is large enough on a classical computer. But at the same time, I want to be clear that we do not believe that quantum computers can solve these super hard problems like things like NP, what we call NP hard problems, which are the hardest problems in this class NP, let's say. Those we do not believe quantum computers can solve. So they're not magic machines either, right? They still have to obey the laws of physics.
So there is a chance to keep like some things that will not break our security.
Absolutely. Yeah. Absolutely. So the whole idea is that, okay, let's say factoring, if we build a large enough scale quantum computer, we're not there yet, then factoring is broken, fine. But then, of course, you move to other crypto systems, right? And there are other crypto systems that are based on more modern assumptions, like lattice-based systems, for example, that are believed to be hard against quantum computers, that are believed to be, unbreakable by quantum computers. So there is a whole field of research now called post-quantum cryptography, which is basically,
okay. I see, yeah.
Imagine we've built a quantum computer, now what do you do, right? You still want a classical crypto system, ideally. The crypto system should be as simple as possible. But it should be hard enough that a quantum computer cannot break it. So that's basically what this field studies. And so what's really neat, for example, is that if you assume this kind of the existence of these problems that are hard to solve with a quantum computer, like these lattice-based systems, then you could do some really interesting things. Like there was a breakthrough result a few years ago that said you can set up essentially a quantum cloud computer. And so imagine the quantum computer is too expensive. You can't buy it yourself. So you license the computer which is on the cloud, which belongs to mega corporation X, and you don't trust mega corporation X. They're trying to screw you. How can you believe that the quantum computer is actually doing what the instructions are sending it, and it's not running some silly program? And it turns out that using these post-quantum cryptography techniques, you can actually verify with very high probability that the quantum computer is doing exactly what you're telling it to do, even if you have no idea how the computer actually works, which is kind of the amazing thing, right?
Okay.
So you don't need any access to the device other than you can send in an input and get an output. And that's enough. So this is something that is generally, well, I don't want to say impossible classically, but it is a very, quantum effect in some sense.
You said if someone can't buy a quantum computer themselves.
Yeah.
I think you don't mean like private person in their home buying a quantum computer, or do you?
Well, I mean, ideally you might want that eventually. Who knows? I don't know, right? I mean, the same thing happened with classical computers, right? Like I think it was in the 60s and the 70s, IBM, for example, which was a leader in, mainframes, and they still are. They didn't believe that there could be a serious home user market. And so that's why they didn't really seriously get into it. And well, look what happened, right? They kind of fell behind, right?
Yeah.
And so even like, there's this quote from Lord of the Rings, which I always like to state, which is that one of the elves is talking to, like, was it one of the hobbits? I don't remember which one. And he basically says something along the lines of, the elves don't like to give advice because, even the wise can't see how all roads will end, basically. Like, all advice can go ill, basically. So, and so, even like people like IBM could missee the future in some sense, right? And now, whether or not we'll have a quantum computer on our desks, right? Personally, I think not. And the reason is not because of something like a technical reason or something like this. Like I do believe eventually we'll get them down to smaller scales, right? The problem is more that a quantum computer, like if you really want to have the benefits of a quantum computer, it typically needs to solve very, very structured problems. Like it's not like you can take any problem in the world and a quantum computer will beat a classical computer. It doesn't work that way, right? There's some problems at which a quantum computer is just really, really good. But I think for many problems, practical problems, the classical computer is still going to beat it, or at least be just as good. So why would you get the quantum machine? It's going to be presumably much more complicated to build, right? So typically the main application for quantum computing is simulating physical systems. So there you want to design a drug, let's say, or nanotechnology or something, and you need to understand how these subatomic particles actually behave. That's very hard to actually study that with classical computers. And so the hope has always been that quantum computers can simulate these systems in a much more direct way, in a much more efficient way.
So quantum computers will not like replace our current machines, but like be an addition to that for specific problems.
So, okay, that's my view.
Okay.
Let's say. I want to be very clear, right? I mean, nobody really knows what the future holds. I tend to take a more, some might call it pessimistic. I like to say realistic, right? Pragmatic. So I do think that, indeed, as you say, it's not like quantum computers will replace everybody's local devices. I mean, these things are much more difficult to build in general. Like they typically need to be kept at very low temperature, at least right now. The energy requirements will probably be much higher. So why would you use that if you have this amazing classical computer like my phone can do all the computations that 50 years ago what one of the giant mainframes could do, right? So, but I should mention that there is a very big push in Germany, worldwide too, but certainly also in Germany. So the German government has pledged, I think, 2 billion euros over the next, I don't know how many years, into the field of quantum computing. A lot of that, from what I understand, is going into industry because they want to fund practical applications of near-term quantum computers. And so in particular, what they're interested in is can they solve certain optimization problems faster with a quantum device than you can classically? And so, examples might be something like if you're a car manufacturer and you have the manufacturing floor and there are all these robots that need to work on the car at the same time, they all have different tasks and you have to coordinate all the different tasks. So it's done as fast as possible and no robots get in the way of any other robot. That's an optimization problem. It costs every second that they saves the money, right? So these are the types of problems that large corporations are currently looking into, like including things like BMW, Boeing, and so forth. Personally, again, I'm not super optimistic on how that will play out, but I think it's a very important first step, because essentially what's happening is these companies are getting slowly involved in quantum computing so that when larger scale computers actually come around, then they'll be ready to really take on the technology and then do something really useful with it, right?
Yeah, I mean, you need the interest from companies
it takes
and
time,
the government
exactly.
do the research.
That's exactly right. Yeah. And typically, I mean, personally, I'm of the view that it's not universities that typically come up with practical inventions, right? It's typically industry, and university does the basic science first, and then industry really takes it to the next step and shows how to apply this in practice and make it really useful and really profitable. And I think that's important, right? We need that help too.
Is there like a quantum computer already in use in a company? And
yeah, there are.
What is it for?
So there are devices. There's a company, the first devices kind of came out of Vancouver in Canada by a company called D-Wave. And so those, for example, I think Jülich has one of these now. For example, it's like a giant black box basically, and you can run experiments on it. Whether it's useful for anything, I think, that's strongly debated. I tend to lean negative, as usual. But there are the devices. They're very early devices, to be fair. To me, the more interesting devices are the ones that are developed in various kind of I guess more like university research labs or on other platforms, like different than the D-Wave platform, right? So like things like Google works with things like superconducting qubits, for example, and they have a very nice platform on which they've done these so-called quantum supremacy experiments recently. So that to me those are, at least I think by many in the field, including myself, are considered a bit more of a serious contender, in the sense that they're really aiming for a universal quantum computer that can kind of do whatever you give it. Whereas, say, the D-Wave ones work in a very specific way, for example, right? Oh, okay. And so they're good for things like optimization problems. At least that's the goal, and that's also why like industry is interested in them, because it's a more restricted computer. I think you can build it on a larger scale, and therefore, you can try to actually use this. So. I don't know what the question was anymore, to be honest.
No, you answered it already, so it's fine. Maybe you can ask yourself, why are there like so specific use cases for different quantum computers? Is it based on like how it's physically implemented, or?
Yeah, I think so. Okay, so ideally you want what's called a universal quantum computer, right? Which is essentially the quantum analog of your laptop. Right? You feed it software, and then it executes those instructions, right? That's what you want. Or you feed it a quantum circuit, like I said earlier, it just runs a circuit. We're not there yet, right? I mean, when I say we're not there yet, we can do it, and again, when I say we, I mean the field broadly, not our group. We don't build these devices. I should mention that the physics group of Christine Silberhorn here, Professor Silberhorn, does build these quantum photonics devices, and she's their group is very good at that.
Oh, okay.
So I could talk a bit about that shortly. That's one of the platforms, photonics, by the way. And I guess this is part of my broader answer here, because we want a universal quantum computer, right? Which is, I don't care about what the platform is. I just want it to run arbitrary circuits,
like current PCs.
Genau, exactly. So when you look at some of these, like the Google platform, from what I understand, like these superconducting qubit platforms, don't ask me what that means, by the way, I'm not a physicist, right? But this is what the technology is called. Those are trying to be universal quantum circuits. And so again, the problem there is you need to keep the noise rate down. It's very hard to control the noise. Now, if you want to do something more limited, you can use a different platforms to do that, right? So the D-Wave computer is basically something called a quantum annealer, if I understand correctly. And it's a very specific type of algorithm that runs a certain way. It's not like you give it an arbitrary circuit, it runs a circuit. It's more like you have a very specific type of input you can give it, and then it runs this annealing process and tries to give you an answer. So it's a very limited setup in that regard. On the other hand, you have things like quantum photonics, which are really good at some things, like they are fantastic for things like cryptography, because you can send like photons across very long distances. Like I believe there have been Chinese teams that have done like these really cool like experiments with the satellites already, like with what we call quantum key distribution. I'm not an expert on that so much, but that's my understanding. And in theory, so in that sense, photonics has played a very important role in quantum computing. And in theory, it's also possible to try and make a universal quantum computer with photonics. But you have to be a lot more clever, let's say.
Okay.
And so, that's kind of one of our goals here, I think, at Paderborn. Together with Professor Silberhorn's group, basically, she's led the foundation of this new institute here. It's called FOX is the acronym. It's Photonic Quantum Systems, basically is what it stands for. And the goal, there's this building they're building in the parking lot. If you have a kid in the daycare or know somebody who does, they might be upset because they're starting to dig up the parking lot next to the daycare. That's the quantum people's fault. So that's going to be the new Fox building, basically. And so there's a big initiative here for that, and it's across computer science, physics, and physics is the leader, and then computer science and math as well. And so together, one of the things we're hoping to work on is trying to do universal quantum computing using these photonic systems. There are other companies who try this as well. Right? We're not the only ones, let me be clear. But yes, there are various platforms. Each has pros and cons.
Okay. So, I mean, it's not the same, but maybe you can compare to like CPUs and GPUs and different like inventions in one computer that like are for specific problems to solve. Maybe you can just transfer to this. I mean, it's not the same. They are not like built completely different. From
that's the thing. That's my concern, right? Like a GPU is basically a CPU with a special purpose in some sense, right? It's probably been very much tweaked to handle certain operations, but ultimately it's still a microchip in the same way, I think, from what I know, right? Whereas a photonics device works completely differently than, say, a superconducting qubit device, for example, right? So it's just one uses like optics, right? It's based on mirrors and lasers. That's photonics. And the other one, I don't know what it uses because I don't know what superconducting qubits are, right? But presumably it's something that's kept very cold, and, that's all I can say about it, right?
Okay, so it's not like we will have like machines in the future where we have like different components with different like physics background, but we try to develop
that probably
these.
Will happen. Yeah, I think you're right about that.
Okay.
But maybe I think the best way to tie this into one of my earlier answers is you asked me, if I don't have a quantum computer, then how do I work with quantum computers, right? And so, like I said, we have this very kind of idealized mathematical model with just like vectors and matrices that we work in, right? And so the question is, how do you actually realize that model in the lab, right? And so you don't have to do it with photons, and let's say, or electrons. You could do it with different types of atoms, and the choice of implementation you choose is kind of not so important, as long as, for me as the user, it does what I need it to do.
Yeah.
So it's a little bit like saying, maybe it's closer to say, suppose you want to run software that, like you want to solve the shortest path problem. You pull up Google Maps or whatever, and you want to know what's the fastest way for me to get home from school, right? I could care less what programming language you use to write the underlying algorithm, right? It could be Python, it could be Java, it could be C. As long as it does what I need it to do, that's all that matters. And this is what I mean. Like you can maybe think of the different platforms as different something like different programming languages. I mean, it's not that, of course.
Okay, yeah.
Because they're using completely different physics. But the point is that, there's two worlds. There's me as the user. I only see the functionality of the device on input-output. And then I don't care how the backend works. You can kind of do it any way you want. Whatever is the cheapest, easiest to manufacture, right? And I think the jury is still very much out on which platform will kind of work the best on a large scale, right? That's still open.
That sounds so interesting. I like this that we also have like this physics side on
Yeah,
our
exactly.
university,
Yeah,
and
I
then
agree,
it comes together, and you can just exchange it. So yeah, it's
So this is it's become one of the core research directions of the university. It's one of the strategic areas we're investing in, basically. So, and like I said, it's not an accident, right? Germany in general is dumping a lot of money into the field, as are many other countries. The US, Canada, Netherlands is doing great as well. So the UK, right? So it's a worldwide effort in many ways, and Germany is certainly running along with it, right?
I heard that you did some breakthroughs and also like provided some papers to some big conferences. Maybe you can talk about that. Like, what are you researching on right now? What is like?
Sure. Yeah. So I don't know. I think it's always weird to classify anything as a breakthrough. I mean, especially in theory, right? So we do study a number of different things. Basically, broadly speaking, we study like algorithms and complexity theory. So algorithms are more, find me a good way to solve this problem kind of thing. And complexity theory is more, find me a way to prove that this problem can't be solved.
Okay.
Yeah. So you want to understand, it's just like a zoo, right? You have your problems and you're trying to put them in different kind of parts of the zoo depending on how easy or hard they are to solve in some sense, right? You're trying to classify things. So some of the most recent works we did, for example, is, so we had this recent paper on dequantization of something called the quantum singular value transform. And, there are a lot of fancy words in the title, but really what this is getting at is it's part of a broader kind of set of works that, we did not start. But, okay, where do I start the story? The story starts, I guess, a couple of years ago when kind of quantum machine learning started to take off as a field. And there are some tasks. And so the really... the canonical example has been there's this, I think it's for Netflix, there's this recommendation systems algorithm that somehow, if it tries to figure out what you're going to like to watch, right? That's what the algorithm does. And I'm not a super expert on this, so I'm going off memory here, how it goes. And so anyway, so there's this quantum algorithm that came out for this problem that claims some quantum speed up over the classical one. And there came this question of whether or not it's better to do possible to do better classically, right? Do you really get this quantum speed up? Is it just that we're just not smart enough to do something classically, or can you really not do it classically?
Okay, yeah.
And so what happened is that the breakthrough was that the field realized that if you give the classical computer just a little bit of extra power, right, then actually it can run the exact same algorithm.
Okay.
Essentially, or it could simulate the algorithm. It could simulate the same results. And this was kind of a breakthrough because, it's helping us understand. I mean, one of the key questions of the field, of course, is, where is the line between what's possible classically versus what you really need a quantum computer to do, right? So finding that line is very difficult because, I mean, a lot of these quantum algorithms, even if you could build a large-scale quantum computer, there's still some other, when it comes to actual implementation details, right? There are still assumptions that are going in, right? So, for example, like, one of the typical things we assume in quantum computing is that if I have a giant database of information, then I could kind of load that all into a quantum computer and do it all in what we call superposition. I can load my quantum memory to hold all the information in kind of one register at the same time. And that is a highly non-trivial assumption. Like, it's not obvious at all how you do this, even if you could build a large-scale quantum computer. And so what these so-called dequantization works were trying to do was that, that's a bit of an unfair assumption to give the quantum computer this ability. So what if we give the classical computer a little bit of an extra ability too? That is a reasonable thing that kind of brings it a bit more evenly on even footing with the quantum computer. And
what kind of abilities?
Oh yeah, so here the ability we're talking about is it's like a sampling assumption, which basically says that you have access to, just like how the quantum computer gets access to this giant database that's stored in kind of superposition, classically we get access to some large store of information, and we can't read it all because it's just way too much information, but we have this magic ability to randomly sample from entries of that information according to how important so if an entry is very important in my database, when I do this random sampling, then I should see that entry with higher probability. So it should kind of give me a hint as to what's important in some sense in the database. And so when you have this ability classically, it turns out that not only can you simulate this Netflix recommendation systems algorithm. So that was a lot of fun. But last year or the year before, there was a very nice paper that showed how to use this whole like dequantization framework to simulate a whole bunch of quantum machine learning algorithms that everybody was like, championing basically, right? And so that's kind of along the lines of what this most recent work has been about. We basically took a problem from quantum chemistry. And quantum chemistry, by the way, I said earlier that one of the main applications of quantum computing is probably going to be simulation of physical systems. And so quantum chemistry is an obvious, example of that, where they're trying to solve problems. And so we showed that there's a problem in quantum chemistry that essentially, if you try to solve it the way the quantum chemists need to solve it in order to understand nature, then you can't hope for a classical simulation. Like you need very high precision, it turns out, in your solution. But if you relax the precision requirement just a bit, then actually you can solve it classically efficiently. So using these dequantization assumptions. And so that was another example of a very nice fine line between what's classical and what's quantum, basically. And so in this case, it turns out just to be a matter of precision. If you want really high precision, it turns out you have to use a quantum computer. And if you're okay with a weaker number of bits in your output, let's say, then it turns out a classical computer probably can do it.
Okay, I see.
This is the idea. But this is a problem that's very specific to quantum chemistry, let's say, right? But it's important to us as a field because to us, we view that as one of the main applications, right?
Yeah.
But to the average person, like, who cares, right? Like, they're not trying to solve quantum chemistry problems, right?
Probably, yeah.
Yeah. So that's an example. Yeah.
I hope that some listeners also are interested now in this topic want to dive deeper into it. Maybe you can say which courses do I have to take if I'm interested in this topic and if I'm a student. Okay, good. So I'm going to give you the same advice that I got when I knocked on my professor's door a very long time ago now. And basically all he said is that you only need to know linear algebra as a starting point. I mean, obviously you're going to have to learn more, but if you really just want to get your foot in the door, you need to understand vectors and matrices. You probably need to understand things like eigenvalues, eigenvectors. And if you can do that kind of stuff, then at that point, you're ready to enter the field, right? Then, of course, you'll learn more about quantum mechanics. And in particular, do not pick up, unless you're a physicist, don't pick up a physics textbook on quantum mechanics because, they will go into it in a lot more depth than we need to, basically. They will model things in a different way, like with infinite dimensional systems. And we don't use any of that in computer science because we kind of model things nicely in a finite dimensional space. But linear algebra is the key requirement. If you want to do computer science stuff, it also helps to have a background in algorithms and or complexity theory, of course. If you like things like error correcting codes, what do they use for that? It's also linear algebra. There are other more fancy tools that are used nowadays, of course. But yeah, let me just leave it at linear algebra and maybe some algorithms and complexity theory is always useful. But you can pick that up as you go. And do you provide specific quantum computing courses? Oh yeah, good. So I do. We kind of offer everything you would need, let's say here, at least from a CS perspective, right? So we offer an introduction to quantum computing course. That's at the master's level. And once you've taken that one, then you can take one of two follow-up courses, which are quantum algorithms or quantum complexity theory. And they do exactly as the name suggests, like it's either algorithms or complexity theory. Those are more advanced, of course. And that's essentially the focus of our group, like those two topics. And so you can kind of specialize in all of that. Of course, you could do other things too, like quantum information theory, which is more like you deal with like entropies and things like this. And, we deal with some of this too in our courses. We'll teach it too, but it's not a hardcore focus of our group, right? So those are the three main courses we offer. We often also have a seminar on quantum computation as well as a more advanced thing you could take. But that's a bit less regularly offered, I think. So it's more like a master's topic. Yes, okay, yes and no. At Paderborn, it's a master's topic. Okay, I see. So normally, and I've tried to have this happen here, but it hasn't been successful yet. And I think part of it is just the statewide laws are kind of difficult to override on how courses are offered, et cetera, et cetera. Normally, the Introduction to Quantum Computing course is offered already at the undergraduate level, but also at the master's level. So you
you do what we call cross-listing, which is that you can either take it as an undergrad or as a master's student, but obviously you can't take it twice, right?
Yeah.
And that way, I mean, you can just take it whenever you want. And I took it as an undergrad. That was very important, actually, in my case. But here, we have very strict rules about no cross-listing, basically, as far as, whenever I've asked to do this, it's been like, no, master's is master's, undergrad is undergrad. Part of the problem is they don't want people getting credit twice, basically, for the same course. All I'm saying is, in principle, you do not need to be a master's student to start. So, for example, I had a really great undergraduate research assistant, Justin Yerka, when I was in the US. He started, I think, in his second year of undergraduate. I don't think he even knew linear algebra at the time, but he was a good student, and he kind of learned linear algebra on his own, basically. And we had a couple of research papers together, the most recent of which went to QIP, which is our top conference internationally. And when I moved to Germany, he wanted to stay in the US, so he ended up going to University of Texas at Austin. So that's where he is now. But the point is that, you don't necessarily have to be a master's student. It's just the main thing you need is mathematical maturity to some extent, right? You need to feel comfortable with math and, not freak out when you see an equation kind of thing, right?
Yeah. I mean, as a student, we always complain about mathematics, but we see it's very important. So
yeah. And that's not something you learn, right? It's just something that takes time. You just I think the perfect quote for this is there's Richard Feynman, who's a famous physicist. He was one of the main inventors of the idea of quantum computers. And I think it was Richard Feynman. No, it wasn't Richard Feynman. It was John von Neumann, actually. And he said, you don't understand mathematics, you just get used to it. And this is 100% true, at least for me, right? I mean, you just see it so many times that it just becomes second nature. And that's when you pick up this mathematical maturity, right? But it's not like I could sit there and predict when it's going to happen in some sense, for each person.
Okay, thank you so much for these answers.
Yeah.
And my last question would be, what do you do now when you return to work?
So today, let's see, what do I have to do? I've got to grade exams we just offered the quantum algorithms course. So that I have to grade exams. And when I'm done that, then I have to work on a couple of different research papers. And I've also got to book travel to, so this year we had 2 papers at this conference, QIP, which is our kind of flagship quantum conference. So one of my students, Dorian Rudolph here, he's going to give one of the talks. So he already booked his travel, and I still have to do that. It's going to be in Los Angeles at Caltech. So let's hope COVID lets us travel. Let's see how. So yeah.
Sounds nice. So thank you so much for being here.
Thank you so much.
Answering these questions. Das war der All-Day Research Podcast, der Podcast des Instituts für Informatik an der Uni Paderborn. Ich bin Lukas Ostermann und wir sehen bzw. hören uns hoffentlich auch beim nächsten Mal wieder. Bis dann.
All-Day Research Podcast. Weitere Folgen findet ihr überall dort, wo es Podcasts gibt. Und natürlich auf der Website des Instituts für Informatik der Universität Paderborn. Wenn ihr immer direkt die nächsten Folgen hören wollt, dann abonniert uns gerne. Dies ist ein Projekt in Zusammenarbeit des Instituts für Informatik unter der Leitung von Patricia Höfer und dem Fachschaftsrat Informatik der Universität Paderborn. Moderation und Redaktion Lukas Ostermann. Technik und Redaktion Alexander Göbel. Sprecherin Sarah Akopian.